Alright, video number 4. We're going to continue on with looking at our two games we talked about in the last video, Babbo and Zambo. And in the last video we talked about kind of playing those two games separately from each other. We talked about playing Babbo and Zambo multiple times and how that really affected the mean and standard deviation for each of them. And we also discussed what would happen if we would add a certain amount, or you could subtract a certain amount from all of your possibilities for your random variable, for your winnings for both games, and how that affected the mean and standard deviation. Now in this video we're going to discuss what happens if you want to play both games together. Okay? And we'll also talk about another example here that we'll look at. Now first off, we're going to start with, what if we want to play a game of Babbo and a game of Zambo? Okay? And we're going to figure out all possible winnings and their probabilities. We're going to calculate the mean of playing one game of each and the standard deviation of playing one game of each. And we're going to assume that each game is independent of the other, that the result of what we get in Babbo has no effect on what we get as a result in Zambo. Now I put this here from yesterday's video to kind of remind me of the amounts that I could win and the probabilities associated with them. Alright, now let's say we first play Babbo, and I'm going to draw a tree diagram of what's going to happen here. Kind of scoot this over so I can get enough room for a tree diagram here. Now let's say when we first play Babbo, we're either going to lose 50 bucks or make 100 bucks. And if we lost 50 bucks and now we're going to play Zambo, there are three outcomes that could happen at Zambo. We could lose 25 bucks, lose 10 bucks, or make 50 bucks. And if we'd won Babbo and then we played Zambo, we either lose 25, lose 10, or make 50. Alright, now let's figure out money-wise, overall, after playing both games. So I lost 50 bucks, I lost 25 bucks, that means overall I'm in the hole 75 bucks. I lost 50 and I lost 10, so I've lost 60. I've lost 50 and I gained 50, so I'm even. Now down here for the bottom branches, I'm up 100 and then down 25, so I'm up 75 altogether. I was up 100 and I lost 10 bucks, so overall I'm up 90. I'm up 100 and then up 50. I'm up 150. So here are, and all of these are different, so I could lose 75, lose 60, come out even, make $75, make $90, or make $150. Now again, it isn't just a matter of this is 1/6, 1/6, 1/6, 1/6, 1/6, and 1/6. Because not all of these were 50-50 chances here. They did not all have equal probabilities of occurring. So now I'm going to write in the probabilities here. So losing 50 bucks in Babbo was a 75% chance, and we had a 25% chance of winning 100 bucks. And now I'm going to put in the probabilities for Zambo. We had a 50% probability of losing 25, a 30% probability of losing 10, and a 20% chance of making 50 bucks. And then I'm going to repeat those probabilities down here. So now if I want to talk about what is the probability of losing $75, well, what would have to happen is I would need for this to happen and this to happen. And since I said that each game is independent, I may multiply the individual probabilities together to figure out the probability of losing 50 and losing 25 in these two separate games. So if I take 0.75 times 0.50, that's going to give me a 37.5% chance that I'm going to lose $75 playing both of these games. Now I just repeat the same thing here following my branches. I lose 50 bucks, 75% chance, and I lose 10 bucks with a 30% chance. Multiply those together and you should get 22.5%. For 0, coming out even, There's a 75% chance I'd lose the 50 first, and then a 20% chance that I would make 50 in the other game. I multiply that together, and I get 15%. And now I come to my 25% times my 50%, 25% times 30%, 25% times 20%. And that leaves me with 12.5%, 7.5%, and 5%. And if I were to add all of these together, I should end up with 100%, with 1.000. Okay, so here is my new probability distribution of playing both Babbo, one game of Babbo, and one game of Zambo. Now, for the mean and standard deviation of this new probability distribution model, this is where you're going to want to use your calculator, and we're going to want to put these numbers into list 1, the probabilities into list 2. Again, to get the mean, we're going to find the sum command and type in L1 times L2. And when you do that, you should get negative $18. So again, this is saying in the long run, if you were to play one game of Babbo and one game of Zambo, and I'll even go ahead and write this down while I'm saying it, in the long run, if you were to play one game, one game of each kind, many, many times, you would expect to make negative $18 on average per round. And by round, I mean one game of Babbo and one game of Zambo. Okay, so if you were to play one Babbo and one Zambo over and over and over and over, sometimes you're going to win 150 bucks. Sometimes you're going to come out even. Sometimes you're going to lose money. And if you took all of those chances, all of those times that you would play one game of Babbo and one game of Zambo, and calculated the mean or the average of all of your winnings, and really all of your negative winnings as well, that on average it would come out to be 18 bucks in the hole. So is it really worth playing these two games in the long run, over and over and over? Absolutely not. Okay? So again, the whole goal of gambling here is the casinos are going to make money. And they're going to make money if you stay there long enough. They're guaranteed by the law of large numbers to get your money. So if you're going to gamble, which I don't recommend, but if you're going to gamble, you are better off gambling in the short run. Play a couple games. If you're up, leave. If you're down, cut your losses, leave. Because chances are you're going to lose even more. Alright, standard deviation. Our command for it: square root, sum, double parenthesis, L1 minus the mean, which is negative 18, so I'm really going to be adding 18, squared, times our probabilities, list 2, end parenthesis for our sum. So this parenthesis and this parenthesis kind of go together. Some of your calculators, if they have the updated software on them, it will automatically put a parenthesis for your square root. So we can put an end parenthesis there. And if you put all that in, it should now give you a grand total of $70.93. Okay. So now, here are the two numbers we just came up with. The negative 18 for the mean, the $70.93 for the standard deviation. And these values here were the ones that we came up with in the last video. That if we were to play one game of Babbo, here was the mean, negative $12.50. Here was the mean for one game of Zambo. And here were our standard deviations. Now here's what I want you to notice. Clear all this off here. When you add two or more random variables, okay, if I had a third game, I don't know what you want to call it, Skip-Bo. Skip-Bo's an actual game, a card game. But if I called it a random variable W, let's say, and I wanted to play one game of Skip-Bo, and one game of Babbo, and one game of Zambo, the same rules will apply for what we're getting ready to discuss here. But notice what both of these added together really makes. This. So if we wanted to figure out this mean, did we really have to go do all of this in the first place? Absolutely not. We didn't have to go that far. If we knew what these were in the first place, if we wanted to know what this is, then all we would have to do is add the individual means. If you add together the individual means, it gives you the really grand mean of doing both things at the same time, instead of them individually like this. Now, you might say, all right, Mr. G, got that? But take a look at this. Do these two standard deviations equal that guy? No, they do not. Because these two standard deviations add up to be, let's see, 4, carry my 1, 3, carry my 1, $93.45, which is not the same as $70.93. So what's going on here? Well, one thing we need to think about is we didn't automatically get the standard deviation first. When we first talked about the standard deviation of random variables, we first talked about the variance, which was the squared standard deviation. And from the variance, we got to the standard deviation by taking the square root. So here's what I want you to notice. That if I take all three of these numbers up here and square them to talk about their variances, so all of these numbers here represent the variances. So if I take $70.93 and square it, it's $50,031.06. Now guess what happens when I add the variances of the individual games together? These two, let's see. If I add those together real quick, I got some room here. Move that up. Get a little space here. So that's 5, 7, carry my 1, 11, 1, 3, 0, 1. Now notice this and this, they're close, but are they exactly equal? They're not. Okay? Now, technically they should be equal. What's preventing them from being exactly the same? Well, this $70.93, this $64.95, and $28.50, those weren't exact values. We rounded those numbers. So those little roundings that we knocked off, that's what's preventing these two values from being exactly the same. Okay, so you will notice there might be a little slight variation in the variances, no pun intended. But really that's what's going to happen here. So really it's not that you can add the standard deviations together, but you may add together the variances. Okay, if you add together the two variances, that it is equal to the variance of the combined random variable, x plus y. So if we want to figure out what the standard deviation is, then what we're going to have to do is basically use a little algebra here, that if I want to go from this to this, how do I get rid of a square? we're going to have to square root both sides. Now, this square root and this square will cancel each other out, but this square root on the right side will not cancel out both of those squares because of that plus sign in between. So it has to stay just like that. If you want to find the standard deviation of two random variables added together, you really have to add together the standard deviations of the individuals and take the square root of them. Oh, really? No, I'm missing something. There should be some squares right here. These squares here need to apply down here as well. Okay, because I just said we can't cancel them out. Maybe I had them there, but they secretly went away. Let's find out. No, didn't have them there. So technically there should be some squares on these guys. So we want to add together the variances of the individuals and then square root that result. Now, what if we wanted to talk about playing Bobo and playing Zambo, but subtracting and figuring out the difference between the winnings? Okay, and you might think, why would we want to subtract these two games here? We might see, is the difference between them, which one's better? Which one leads to a higher difference? In terms of differences, it's kind of hard to find a specific example that works well for adding a specific value, multiplying a specific value, adding together two random variables, and subtracting two random variables. This is going to be the one example that, if you really think about it realistically, not going to make a whole lot of sense, but we're going to go with it because we will talk about other examples of subtracting random variables. So we're going to do the same thing here. Keep in mind, Bobo, we could either lose 50 bucks or make 100 bucks. Zambo, we could be down 25, down 10, or up 50. So if I were to do a tree diagram again, but now, instead of adding these values, I want to subtract them. Okay, so here's what's going to feel a little odd here. We're going to be subtracting all these numbers. So really, when I subtract a negative 25, this is really going to end up giving me negative 25, because I'm really going to be adding 25 to a negative 50. Here I'm really going to be adding 10 to a negative 50. So here I'm at negative 40. Here I have 50 minus another 50. So there's negative 100. Here's going to be 100 minus a negative 25, which I'm really going to be adding it. So there's 125. Here I'm really adding 10 to get 110. And here I am subtracting 100 minus 50 is 50. So here are my possibilities here. Here's those three right there, followed by my next three there. I just decided to go in numerical order from least to greatest. And we would do the same thing with the probabilities that we did earlier. We're actually going to get the same exact probabilities because we're still going to be multiplying the same exact way, except they are tied to different numbers now. Okay, so this negative 25, that was the first one we did earlier, and that's when we had, I'll go ahead and write it in here, this is when we had 75% times 50%, and that gave us our 37.5%, which is what I've got right there. So I just find the corresponding probabilities from the previous example and fill it in appropriately. Okay. So now, if I wanted to find the mean and standard deviation of these, again, let's go list 1, list 2, or you can use list 3 and list 4, it doesn't really matter. For the mean, we're going to take the sum of L1 times L2, and you should get negative $7. There's a negative $7 difference between the winnings in Bobo and Zambo. And if we were to do standard deviation, well, I can figure out how to do a square root here. We're going to do the sum double parenthesis, L1 minus, we're going to subtract the mean, which is negative 7, so we're really going to be adding 7, squared times L2, end parenthesis, again, where this parenthesis and this parenthesis are trapping all of this in there, and we get $70.93, which looks kind of familiar. So now, here again are the individual values for means and standard deviations for a game of Babbo and a game of Zambo. If I were to take these two numbers and subtract them, because that's basically what I'm saying here, if I were to take negative $12.50 and subtract a negative $5.50, well, I'm really adding $5.50, and guess what negative $12.50 plus $5.50 ends up being? Negative $7. But again, if I subtract my standard deviations here, well, let's see, that's 5, that's 4, let's see, $36.45, which again is not the same as that. So when we talk about means, if we want to subtract and do this overall, this new random variable x minus y, we don't have to do, again, all of this. This is completely unnecessary. Because all we really have to do is just add our individual, or not add, subtract our individual means here. Oh. Put this up here. All you have to do is subtract the Babbo mean, subtract the Zambo mean, and that's the same as doing the whole new random variable x minus y. Now, standard deviations, we just said not going to be simply just subtracting. Again, let's look at the standard deviations by looking at the variances. So again, these are the variances. But if I subtract these two numbers, I know I'm not going to end up with 5,000. Okay? We can never truly subtract standard deviations. Okay? Standard deviations may only be positive values. That was a property of standard deviations that we once upon a time talked about. So if we get the same numbers here, we know what's already going to happen based on the previous example. We know these two things are going to add together to equal this. Okay? So whether you're adding or subtracting random variables, the standard deviation is always going to be the addition, the sum of the variances, and then the square root of that. Okay, so that seems a little confusing. Again, I need to put in my squares here. We are really adding the variances of the individual probabilities, or the individual standard deviations, sorry, and then taking the square root of all of that. Because again, if we square root this and square root that, this cancels off, but this over here does not cancel off. These squareds do not cancel out with the big square root. And again, it's because of that plus sign in between them. So for adding and subtracting two or more random variables, this is one thing you must make sure is mentioned. The random variables must be independent for the rules of standard deviations to apply. So the only time that you may do this is if x and y are independent. And the only time you may subtract the combined random variable. And again, it's the same exact formula. Whether you're adding or subtracting, it's the same thing. But again, it's only if x and y are independent. If there's no mention of x and y being independent, You can still calculate the mean, but you may not calculate the standard deviation. Okay? So, if you have any questions, hopefully you wrote something down, and we will practice more with these in class the next day or two, I believe. All right, good luck.